So just to review, in case you haven't been looking at the schedule for next week, exam 1 is on Wednesday. It's in here. You will need things like calculators, pencils, paper. Well, no, you don't need any paper. I provide the paper. So calculator's okay. No phones, no computers, nothing, no books, no phones, etc. You do, however, get 1 page of notes. And so just because this has come up in the past, a page is defined as an 8.5 by 11 piece of paper. Single ply, that sort of stuff, so you don't get to, like, I don't know, fold up a book or something like that. You can write anything you want on there. You will turn that in with your exam. You'll get it back, obviously. Ton, yes, ton. Turn in. With the exam. Practice exams have already been posted. They've been up all quarter. In terms of content from the practice exams that would likely show up, you're definitely in exam 1, and you're partway through exam 2. Basically everything that was covered up until Friday, 3 days ago, that's all fair game for this particular exam. So nothing starting today onwards will be on that exam. So all single reaction stuff, there will be no multiple reactions.
Professor, to clarify, that's going to be lecture 1 through 10?
That sounds correct. I forget what lecture we're on today. No, I think that would be like 1 through 8, because 1 through 12, because we have 4 a week. Something like that? Yeah.
Is there a limit on what we can write on that paper?
You can write anything you want. Sorry? Because I want to see what you wrote. Yeah. Yes, you can write on both sides. Hang on just a second.
Would it be okay if I wrote on a single-sided piece of paper?
Yeah, as long as you, you're going to turn it in. So if you prefer to have 2 pieces of paper, but one just on the front on both, that's fine. Sorry, yeah, go ahead. Possibly. The question was, will there be MATLAB code on the exam? That's possible. If you want to see an example of what that looks like, there's a practice exam that's got MATLAB code on it. Yeah. Your notes? No, they do not have to be handwritten notes. If you'd prefer to type them up, that's fine. Let's see, anything else about, I guess I should put that up there since this is being recorded and will be posted. Covers up to last Friday. So in terms of content, that's all the way up to non-isothermal reactors. Everything today, as I mentioned before, and the rest of this week is not part of that exam. Anything else I should mention about the exam? Any other questions on the exam? If you want an idea of like the length of the type of questions that I ask, again, they're going to look pretty similar to what they were last year. I don't think I have anything else to add about the exam. By, I think, end of next week, we should be able to talk about the project because we'll start on our flow reactors next week. The project is all about flow reactors. So there'll be more details on that next week. Before we get to today's content, anything else? Any other questions on that?
Professor, he's asking the next Wednesday, right?
For the exam? Yes. So like 9 days from now, not 2 days from now. That's a good point. Wednesday of next week. I will supply all the paper, so you don't have to bring any of those little blue books or anything like that. I will have paper for you. I think that's it. Feel free to ask more questions as we go. We still have time. Happy to answer any other questions. Our topic for today is kind of the last quote-unquote new topic that we have for most of the course. So we've been introducing new concepts as we go along. The energy balance was kind of new, right? There were elements of that were new, but it was very similar to the energy balance that you would have derived in 100 or 102 for that matter. The big change that we had was in the material balance, where we introduced that new term for rates. And that's where we have to go when we deal with multiple reactions. And so that is our topic for today, which is multiple reactions. So multiple reactions. The concept of multiple reactions should be somewhat similar to anything that we would have seen previously. So what we mean by multiple reactions is something like, those are some of the, you ever see, does anybody look on Reddit? There's a penmanship subreddit, and every once in a while you get a really nice symbol or something. That's a really good reversible reaction. Like the lines are straight and everything. Oh, it's been screenshotted already. Yeah, it's being recorded. So this is technically a multiple reaction. So we have been dealing with multiple reactions. It was just a special case of a reversible reaction. The other way that you could write that would be an irreversible reaction of A goes to B plus P, B plus C, and then another reaction of B plus C goes to A. We don't really, when we say multiple reactions, we mean at least more than one of those. So if this were reaction 1, a multiple reaction system would have at least one more of those. And it could look something like C goes to 2A, or whatever it happens to be. And that's what we mean by a multiple reaction system. There's no clever way like we have with a reversible reaction, actually that one's not bad either, to write them as a single reaction. And it also does not matter if they are mixed. So for example, if you had yet a third one on here that was irreversible, 3B goes to something like 2C, that's fine too. It can be any number of any type of reaction, whether they are irreversible, reversible, doesn't matter. It can be any mixture of those. The way that we typically dealt with these in something like CENG 100, if you had multiple reactions, which I think you did on one of your projects, would be to give each one of these their own squiggle and to denote the squiggles by the number of the reaction. So each of these would get their own extensive reaction, squiggle 1, squiggle 2, squiggle 3. And then if we wanted to know how the moles of any particular species changed, we could write that the change in the moles of any species I, delta Ni, was the sum of the stoichiometric coefficient of species I in reaction J times the extent of reaction for species J, or reaction J. And so this would get summed from J is equal to 1 over however many reactions you happen to have, which is normally given the letter Q. This can also be M. Sometimes you'll see it as a sum over all reactions. J is equal to 1 to M. It's the same thing. You sum it up for every single reaction that you happen to have. And then the way that we would go about solving these is we would give you a bunch of extra information, just enough that you could solve for squiggle 1, squiggle 2, and squiggle 3. And that's how you would go about a multiple reaction problem in something like 100, or even into 102, if that happened to come up at all in 102. The approach here still works for 113. The problem is, as we saw previously, this doesn't tell us anything about time. So all we can do is say what happened to the reaction before and what happened to the reaction afterwards. We can't say anything about what happens to the reaction as it's occurring, and that's where our rates come in. So the change in approach that we have from 100 to 102 is the following. The general approach for one of these, and we'll look at some of these steps in more detail. So the general approach for a multi-reaction example in 113, specifically for the material balance, we'll worry about the energy balance later. The first step is to number the reactions. again, usually from 1 to whatever. And I'm going to use J. Like I said, for some reason your book decides to switch from I and back and forth to J, which I think can be very, very confusing. 1 all the way out to Q. Typically in something like a homework problem or a project or an exam or something like that, I will have probably numbered them for you, but you are allowed to renumber them if you so desire, or if somebody has not numbered them and you would like to number them, you can always do that. Step 1's easy. Step 2 is not too bad. It really hasn't changed from week 2. Step 2 is to write a rate law for each reaction. This is kind of the step where you have to make the first choice. Like Bob Ross says, we have big choices to make for this. You have to make a choice, and that choice is which species do I want to write it for? You know, whatever the species A is. That may not always be possible to choose the same species for every single reaction. So if you flip back or look up in your notes, for example, we cannot write a reaction for species A for every one of these reactions because A does not participate in reaction 3. So it becomes a question of which one's the most logical species to choose for each one of those reactions. It may not always be possible to do it for all species, which is fine. The way that those reactions tend to get written, leave a little space below this because I'm going to indicate those I's and J's. It's the same old reaction. Ij is equal to, that's supposed to be a lowercase k. Let me make that a little bit smaller. Some rate constant k followed by some function of Ca, Cb, all the way up to concentrations of species I. I write that as a general sense as some function of all of those. We've only learned how to specifically write one for an elementary reaction where we take the product of all of the concentrations raised to their stoichiometric coefficients. That's what I mean by this function over here. If it's non-elementary, then I just give you that particular function. Yeah?
Should the A in the rate law that you're using be the limiting reactant?
Not necessarily. So some reactants will, or some reactants will only occur in some reactions, even if they were never fed to the system. So they can be produced partway, like intermediate as the reaction is occurring. Some things will get produced then, and we could count those as any other species that we want.
And you write the A as the, you use the product as the A that you're basing everything else on?
Well, so that's the thing. The A can change from one reaction to another. You have to pick whatever's most reasonable for that particular reaction.
Will that particular reaction's A be the limiting reactant?
No, not necessarily. No. You'll also see that that's why we stopped talking about conversion of species A as a tool to help us solve any equations, because we can't write all the equations in terms of the conversion of A, and so we stop using it. We can still calculate it when we're all done, once we've figured out what everything is doing, but we will no longer have expressions as a function of conversion of a specific species, because we can't write it for everything. And that gets reflected in the next step. So the elements that I've got here, so this is species I. Again, whichever one seems most reasonable. Sometimes you won't have a choice. Sometimes I will give it to you in a particular form, and it'll be obvious from whatever the subscripts are. And then the subscript J here is for whatever reaction you happen to be talking about. And you'll see different ways to represent something like that. Sometimes the little k on the other side, it just depends on who you're looking at. Sometimes the reaction rate, or reaction constant, rate constant k, will look like Kij, right? They'll give you both the I and the J, which is trying to tell you how to write that rate law. Sometimes it'll be just the J. Sometimes they won't even mention the difference between the Ks. They'll just list the K at each reaction, and then you have to number it. But there should always be some indicator as to which reaction is associated with which K. There's just multiple ways to do something like that. And then these C's, most of the time, not all will appear. That's why I wrote this as some general function and not a specific function. it's not necessary for all species to participate in all reactions, nor all reaction rates to depend on all species. Oftentimes we will assume that these things follow elementary rate laws, and so we can write those forms in a pretty straightforward fashion. So we have to write that rate law. The key point here is that we only did this for one species. We need to know the rates for everything for all reactions, but when we start off with the rates here, we just do it for one species. Pick whichever one seems most reasonable, particularly if somebody gives you that rate and says, for example, if you had something like this, the rate of consumption of B is in reaction 3 is equal to minus K times something, something, something. Use that as whatever the species is that you're going to write it in. Yes?
What are the M's and F's? I don't think I thought that.
Up here on the top, some books you'll see they sum from J is equal to 1 to Q. Other books will say J is equal to 1 to M. They mean the same thing, the number of reactions.
Thank you.
Yep. So those are these two steps seem kind of straightforward. This is the next one where most of the mistakes get made. It's easy to write. It's a little bit harder to do in practice. It just takes a little bit of just that, practice. So the third step is to write what's called a net rate. For each species. And I'm going to underline the word species there, because usually the mistake that gets made is that someone will try to write a net rate for a reaction, which doesn't really have a definition. You can't write, I don't know of a way to even define a net rate for a specific reaction. So the net rate comes for the species. The way to write that net rate is the part where, again, it's pretty easy to write down in this form. It's a little bit more of a bookkeeping exercise when it actually comes time to write it. So the net rate of species I is just equal to the sum of the rates of that species I for all the reactions. Right? That doesn't sound terrible, right? I write a rate for each one, and then I sum up the rates for each species, and that's the net rate. But it can be a little bit confusing if you try to do something like that for a reaction, because it's very hard to define something like that. Like I said, I've never seen one defined that way. In order to do something like this, we have to know how to link what was in step 2. So step 2 said, write the rate law for each reaction for one species. How do we extend that to multiple species? We use the relationship for stoichiometry that I had briefly mentioned, I think back in like week 2 or something. I said, we don't really need this very much right now, but we're going to need it a lot in any kind of multiple reaction system. This is what I'm talking about. So generally, the rate of any species I in reaction J divided by the stoichiometric coefficient of species I in reaction J is equal to the rate of any other species I, which now that I sit here and think about it, I'm going to need another, let's do K. I need another subscript, and I've run out of subscript. Any other species K in the same reaction divided by the stoichiometric coefficient of species J in the same reaction. So let's summarize those subscripts. The subscripts I and K here are species in reaction J. So the way that we've seen this written before was something like the rate of A over minus little a is equal to the rate of B over minus little b is equal to the rate of C over little c, and the rate of D over little d, right? That's what we are referring to. It just has a more complicated look because now we have one of these relationships, these, or this, it's the same thing. We have one of those for every single reaction. And that's how we relate writing the rate law for a single reaction, for a single species, into net rate for that species for all the reactions. Another place that is typically a source of mistakes is the nu sub I here. It's very easy to get those confused from one rate or one reaction to another, but they're always for a single reaction, never for multiple reactions. Once you're done with those two steps, you're about 90% of the way there. The last step is to solve the material balance. And the material balance is written for a species, right? We always write material balances for species, never for a reaction. And so the total number of moles, the rate of change of moles with respect to time is given by the net rate, R sub I, times the total volume. So the R sub I here is the net rate from step 3. The V is normal. We don't change the V at all. You could also potentially write, and I'm going to have to do this in, I guess, green since I've run out of, actually the gray shows up, okay. The other one that you can solve is the other version of this, which is the concentration of I changing with time is equal to R sub I. Right? Either one of those are fine. And you're going to have one for every single species. There's usually not, unless somebody went out of their way to make the problem solvable by only doing one, you typically have to write one of these differentials for every single species. Because the rates of one of them will typically be dependent on the rates of all the other ones, or the concentrations of all the other ones. And so you typically have multiple differentials to solve. And so you're back to a case where you have to do something like MATLAB and solve a set of coupled differential equations, one for each one of those species. Notice what's not on here. The one that's not on here, which I'm only going to write over here in blue, and I'm not even going to complete it, is that you won't find a differential that looks like this. You won't find any differentials in terms of the conversion of something as a function of time. The reason being it becomes quite a headache to try to represent that theta I plus stoichiometric coefficient of I over stoichiometric coefficient of A times XA for everything. In fact, I'm not aware of actually a very general way to do it. There are some instances for a simple set where you can do something like that, but it becomes a pain in the neck, and ultimately you end up solving the thing in MATLAB anyway. So it's almost invariably, certainly in this class, invariable that you will have differential either in terms of n sub I, which is this one, or Ci dt, or generally Ci, for this particular class. Those are the only two differentials you're going to solve. You're never going to see one like this for a multiple reaction system. And that's it. That is the major change between what we have done previously and what we have done now. The net rate thing is usually the part where the mistakes get made. The step 4, solving the differentials, usually goes okay. Any of the mistakes that get made there are the same as the ones that would get made in any other coupled ODE system. Not indexing correctly in MATLAB or something like that. But that particular step, if you're comfortable or if you become comfortable with the coupled ODEs with the energy balances that you're working on right now for this homework, this is not going to change that very much. So I will, just as an example, what this tends to mean is that variable y in MATLAB the one that I always refer to as uppercase y, that will start to look like, for example, moles of A, moles B, moles C. And if you have both energy balances to consider and material balances, then you get an additional one for temperature. And as we will see with flow reactors, there's more for pressure and for coolant. We briefly saw coolant on Friday's lecture, the coolants usually become more relevant when you're talking about flow reactors. So you end up having very large sets of differentials to solve. And so your other expression that goes in the ODE function, the one that looks like dy dt, this is going to end up looking like a column vector of dNA dt followed by dNB dt, etc., all the way out to as many of those as you have. Surprisingly enough, it has almost no effect on the speed at which MATLAB can solve these things. So don't feel like suddenly with multiple reactions we're dealing with computations that take an hour or something like that. Most likely it will still finish before you can blink after you hit run, which is pretty cool. It's very fast. But that's the major change in MATLAB. Beyond that, it doesn't change too much. It certainly doesn't change the template. So the template that I gave you for coupled ODEs, same template. Works for this regardless of what variables are coupled. It'll handle all of them. So let's look at an example of the net rate, because again, that's where it usually comes up. So the example to which I'm referring to is the same one that I just gave at the beginning of the lecture. So if you don't want to write this again, you don't have to. I'm going to write it again so that I don't have to refer to it over and over and over again. So it was A goes to B plus C, and that was reaction 1. Then we had C goes to 2A. We called that reaction 2. And we had another one of 3B goes to 2C. And we call that one reaction 3. So if we're following that pattern, we've kind of got the first step done, which is number the equations. We've got 1, 2, and 3. We need to write a rate law for each one of these in terms of one of the species. So I'm going to assume that all of these are elementary. And I'm going to assume that they're all written in terms of concentration. You can still do, none of this changes if you're doing concentrations or partial pressures. It's rare that you'll ever see a mixture of the two. If somebody gives you a rate law for one reaction in terms of concentration and one in terms of partial pressure, you're probably in a situation where you have multiple phases present. And so the gas phase usually goes along according to the partial pressure and the liquid according to the concentration. If you see something like that, switch it all over to one of them, pick one, usually the concentration, or moles, you could do that one, but you're not going to have any mixtures in this class. Mixtures, I mean, of concentration rate laws and partial pressure laws. It'll always be one or the other for a problem. So let's take reaction 1. And so for reaction 1, the magic species A, the one that I want to write everything else in terms of, I'm just going to arbitrarily pick this as species A, since it happens to occur in something like that. And if I write the rate law in terms of that, normally we would write this as the minus the rate of A. The 1 that follows there is the reaction, is equal to the rate constant K of species, or of reaction 1. And then what did I write? Concentration of A minus concentration of B, concentration of C, divided by equilibrium Kc. Anything squared in there? No. So if you're keeping track of the steps, these steps up here, that was step 1 from that method that I have a minute ago. This was step 2. And then step 3 is to write everything else that takes place in that reaction in terms of this particular rate. So if I wanted to be verbose with everything, that would be the rate of A in reaction 1 divided by its stoichiometric coefficient, which is -1, is equal to the rate of B in reaction 1 divided by its stoichiometric coefficient, which is 1, is equal to the rate of C in reaction 1 divided by its stoichiometric coefficient, which is also 1. So this is step 3. Often I will not actually write out every single one of those because it gets kind of tedious to write that equation 3 times with nothing but like a coefficient or a negative sign sitting out front. Did my mic just die? Yeah. There was a question over here. No? Must have been a stretch. It's that Pavlovian response again. If I see a hand, I assume it's a question.
I have a question.
Shoot.
The original example you gave in the beginning of class was, number 3 was a irreversible reaction. Does it matter?
Ooh, yeah, good point. That was supposed to be irreversible. Let's be consistent and keep it irreversible just so that we have some level of continuity. Ultimately, no. It's whatever the reaction happens to be. The only difference would be on this particular term. An irreversible reaction usually does not have a term that looks like that. But in terms of going through that 4-step process, won't look any different. So at best, we could call this 3 part 1. Right, because we're going to have to repeat this for every one of them. We also have to repeat part 2, or step 2, many different times. Typically, this is the pattern that I follow, which is to do step 2 followed by step 3 for one of the reactions, then step 2 followed by step 3 for another one, then step 2, then step 3 for another one. It really does not matter if you would prefer to just knock out everything for step 2 and then go on to step 3. You'll end up in the same place. I'm just in the habit of doing it in this particular form. And so that is for reaction 1. If you're good with following steps, you probably know where we're going for reaction 2. So for reaction 2, we again have to pick whatever magic species of A that we want. And so for reaction 2, I'm going to pick species C as this special A, even though A itself shows up in that particular reaction. If you want to keep it A everywhere, that's fine. I'm in the habit of always picking one of the reactants as one of the special ones, just so I don't get confused as to whether or not the negative sign comes along. So if you had chosen, for example, A for reaction 2, then you would not have this negative sign. Right, because A appears as a product in reaction 2, not as a reactant. For me, I get confused if I keep flipping back and forth, so I always pick one of the reactants as species A, even if species A happens to appear in that reaction. That is entirely my preference. If you would like to go the other way around, that's fine. You'll just have a negative sign difference floating all the way through. Question up there, Ernie?
It's not actually referring to that. Can we just multiply it by 2 and then we get C?
Be very careful moving the stoichiometry around. Most of the time, yes, you can play around with the stoichiometry as much as you want. The challenge becomes, if you're going to do it before you do anything else, and then follow that stoichiometry through the whole problem. Don't mess with it halfway through, because then a lot of your deltas will refer to different stoichiometries, and you can get different answers that way. So yeah, totally okay, but if you do it, make sure you do it first. Exactly. So for the rate for this one, I would write that minus the rate of species 2, or species C in reaction 2, is equal to the rate constant K for reaction 2, and that one we had a reversible one. So that would be concentration C minus concentration of A squared, yeah, because we went to 2A, divided by rate constant Kc. And actually, I think I made a mistake in the previous one. These equilibrium constants have subscripts on them as well, because the equilibrium for one reaction is not the same as the equilibrium for the other one. So flip back up in your notes to that reaction 1. Yep, sure enough, this needs to be Kc1. Because the correction I just made was right here. That needed to be Kc1 for reaction 1. Let's see, I think that is all that we need to do for the rate here. Again, if you wanted to do that rate in terms of A instead of C, that would be fine. It'll be a little weird as you go through it. So that would be step 2. Step 3 is to write the rates for everything in terms of everything else. So the rate of C, according to reaction 2, over its stoichiometric coefficient is the rate of species A over its stoichiometric coefficient. Yes?
That should just be a 2, right? Not 2.
Oh, yeah, thank you. I don't know why I put that there. And this should also be R sub A in reaction 2. And that's that. You can probably guess where we're going with reaction 3. We're going to do exactly the same thing. I am going to move this and just put my reaction 3 right underneath it. It lagged there for a minute. I was really afraid that was going to crash my iPad. So for reaction 3, again, we need some species A, whatever we want A to be. Whatever we want A to be, and I was going to choose B anyway. I'm so clever. So the rate of B in reaction 3 is equal to the rate constant for reaction 3. That one was irreversible. So we're going to have that rate constant times the concentration of B cubed. If that were the reversible one, there would be additional terms that follow along.
Professor, did you write it reversible on the other slide?
I did. The very first slide I did, I came back a couple of moments ago and fixed it here, just so it's consistent with the very first slide. But I did have to change that to irreversible. And then the balance of the rates here, again, the rate of consumption of B in reaction 3 divided by its stoichiometric coefficient, which is -3, is equal to the rate of generation of C in reaction 3 divided by its stoichiometric coefficient, which was +2. So you can see the pattern follows pretty nicely, but it's very easy to make mistakes along the way if you mix up which stoichiometric coefficient goes where, and whether or not things have negative signs in front of them. So find a pattern that works for you. I find this one works almost all the time, so I recommend it. So that was steps 1, 2, and 3. Actually, I guess that was more like 1 and part of 3. We haven't actually written the net rate for everything, so we have to do that. So net rates. Until you're very comfortable writing net rates, I suggest you write them out longhand. I still make mistakes writing net rates, so I still find myself writing them out longhand. And I usually start with the definition of a net rate. So the net rate of A is equal to the sum of all rates of A in each reaction J, summed up from 1 to Q, however many you happen to have. So we have 3 reactions. So the very first thing I do is write all 3 of those rates without trying to make any substitutions at all. So if I write that out longhand, that means rate of A in 1 plus rate of A in 2 plus rate of A in 3. No sign changes get applied, nothing like that. I'm just using that definition, writing out that the definition of the rate of A is the sum of A in all of the individual reactions. And this is where I then go through and find out if anything is 0. I write it in terms of all of the reaction rates that I had previously seen, one at a time. This is a lot easier if you have them written down in your notes than what I'm going to do here, because I have to switch back and forth. So to try to illustrate that, I'm going to use different colors for each one. So rate A in 1, I have to go look up what my rate was for reaction 1. More specifically, I look up what did I write the rate in terms of. So I happen to write the rate in terms of RA1. So I don't need to rewrite that in any way, right? I don't need to use this stoichiometry down here because I already wrote the rate in terms of A1, or in terms of A for reaction 1. So I'm going to leave that alone over here and just say, okay, that is RA1. The reason I left it there is because I've already got the rate in that particular form. That'll become more obvious when we see what it looks like in MATLAB. Then I have to look up, all right, what's the rate for species A in reaction 2? So reaction 2, we wrote over here. We wrote this reaction in terms of RC2, and so we have to use the stoichiometry here in order to go from C2 over to A2. So according to this stoichiometry, RA2 is going to be equal to 2 over minus, was it 1? Yeah, minus 1 times RC2. So that is the rate for species A according to reaction 2. And this is what I'm going to write over in that slide that I'm about to switch over to. So I'm going to write minus 2 RC2. Let's see how long I can keep that in my working memory. Minus 2 RC2. Did it? And then I need to do the same thing for the third reaction. I have used blue, yellow, I guess green is the last one. So for the third reaction, I'm going to flip over to my third reaction here. And notice down here, there is no A. Which is, there's kind of an imaginary A sitting there. The stoichiometric coefficient of A is 0 for that reaction. The same as if there's an inert that shows up anywhere inside here. The stoichiometric coefficient there is 0 for everything. We usually don't write an expression like this for something that does not participate in that reaction because it doesn't really work out, right? You end up having a rate over a 0 when we really mean that the rate is actually 0. But because there is no A that occurs or participates in reaction 3, when we get over here, we just have a plus 0. Because there's no A in that one, exactly. So again, this is all equal to R sub A. So then if you want to go one step further and work all of that out and make it look consistent in a particular color, 2RC2. So this is the net rate then for R, or sorry, for A. And that's exactly what our differential will say, right? If we wanted to do this in terms of, say, I don't know, concentration, something like that, then over here we have dCA dt is equal to all of that, with the same kind of initial condition that we would have had before, which is that at time 0, the initial concentration of A is Ca0. Or if you're going to use moles, that's fine. It would look like dN dt is equal to all of that stuff. So this is what we mean by the net rate. There's plenty of places along the way that we can make small math errors. Mostly my mistakes come from not subscripting things. You saw I forgot the subscript on a K. That's a pretty common one. This step is a pretty common mistake here. Because until you've done it a couple of times and it becomes routine in your mind, it's easy to start mixing those around, right? If A is showing up in multiple places, it can be a little hard to track down. The negative signs can initially seem a little bit confusing, which is also why I always follow that pattern of the first step there, which is to just write out that definition of a net rate as the sum of the rates. If all of that seems totally normal to you, then great, you're in good shape. But it is easy to make small mistakes along the way. So since this is an example, I will write the other ones. It looks like we won't quite have time for the last two. Sorry, we'll get to them in the next. Yeah.
Can you give some like what assumptions are made for this calculation?
Not a single one. We have used nothing but stoichiometry right now.
So is the volume constant?
Volume can be varying or constant to do something like this. I guess there was one assumption that we made here when we wrote that rate law, but that has nothing to do with the pattern that we were using. You'll notice when we skip to, when we actually do this step, those rate laws could be anything, right? They could be 9 lines long or whatever they happen to be. That particular relationship still works all the time. And conveniently, that's one of the very few things that will have no change whatsoever when we look at different kinds of reactors later in the course. This step will always look exactly the same. So if we want to write the net rate for B, the net rate for B is the sum of the rates of B in each equation, or each reaction J. So that's RB1 plus RB2 plus RB3. And if I want to go back and look at each one of those, I'm going to have to flip back and forth. Actually, to avoid, yeah, well, we'll flip back and forth. We might as well. So if we start with the first reaction, we have an RB1 here. And we wrote the entire reaction in terms of A, so we're going to need that stoichiometric relationship. Fortunately, it's just a negative sign. So RB1 is equal to minus RA1. So that's what we'll put over here. RB1 is equal to minus RA1. RB2 is going to be 0 because B does not participate in reaction 2. And RB3, if you look at the stoichiometry for reaction 3, stoichiometry says it does, or actually looking at the reaction, it does definitely occur. But we wrote the rate law in terms of RB3, so we're just going to leave it as RB3. We don't have to do any modifications. So this looks like RB3. And then the last one, so this is rate for B3. The rate for C is the sum of C for each reaction J. So RC1, RC2, and RC3. C in reaction 1 will end up being minus RA1. C for reaction 2, we wrote it in terms of C for that one, so we don't have to change that one. It's RC2. And C for reaction 3, we wrote that one in terms of B back here. So here's our RC3. And so we're going to end up having minus 3/2, or sorry, other way around. Minus 2/3 RB3 is equal to RC3. So minus 2/3 RB3. Keep that in my working memory. Minus 2/3 RB3. So now we have our net rates for every one of these species. And so we end up then solving DNA, dt. Actually, let's do C. C is a little bit more convenient since everything was written in C, which would only typically work if we have constant volume. dCB dt is equal to RB. And a third one, dCC dt is equal to RC. Notice there are no negative signs floating around anywhere in our material balances. You'll see we didn't have those the first time we derived those or defined them. There were no negative signs in there. All the negative signs are handled when you're writing these sum procedures here and here. So don't start adding negatives in there because you think they need to be there. Let that step of writing the net rates dictate whether or not things need negative signs or not. Yet another place where mistakes commonly happen. And so we'll get to a quick definition tomorrow, Wednesday, of some various things that happen in multiple reactions, and then we'll just look at a few examples for the rest of the week. Could I get all those homeworks back, any uncollected homeworks back? And that's all I've got, so have a nice day. I'll see everybody on Wednesday.